Guys, want to make a quick video about something called apparent weight, right? So we already talked about buoyancy a bunch, and you know, if we take this block here, it has a certain weight, and we submerge it in water, we know that that water is going to exert a buoyant force on it in the opposite direction of its weight, right? Weight is down, buoyant force will be up. It's like the fluid is helping it, right? So things underwater don't feel like they weigh as much, right? And that's because of this buoyant force. This is why NASA uses a gigantic pool to train all of their astronauts for spacewalks, right? Things underwater feel like they don't weigh as much because of that buoyant force, and so they have this gigantic pool where they train because it simulates 0G. So back to this problem, right? If we suspend this block in air, it looks like it weighs 7 pounds. We're going to use pounds just because we all understand this. Now, if you submerge it fully, then it is going to take the place of some of the water, right? The volume of water that will spill out is equal to the volume that this block takes up. Okay. And what happens is the scale suddenly reads less. It reads only 4 pounds because there's this buoyant force that's like it's helping it. Okay. The water that comes out will represent that lost weight, right? And so this 4 pounds right here is what we would call the apparent weight of the block. The actual weight is 7. Okay. So to do this, the math is very easy. There's an actual reading before you put it in the water. Okay, so it has an actual weight. When you put it in the fluid, the reading on the scale goes down, and that's called the apparent weight. Yes. And there's a little bit of water that is displaced because now some of the water has to move aside for this little ball here, right? And that amount of water is the volume that thing takes up. And that buoyant force, that upward force, okay, is what is creating this illusion that it's lost weight. So the equation that we use is the apparent weight is equal to the actual weight minus the buoyant force. So this apparent weight is what you would get if you take the bigger reading, the actual weight, subtract that upward force of buoyancy. Okay. So we're going to try a little problem here. Here I've got a beaker, and there's something, look like a rock, and it's suspended. Let's say that there's a little spring scale that's holding it, right? And it's filled to the very brim with water. And when we put this thing into the down into that beaker, some of the water overflows. The mass here, this rock, has a mass of 3 kilograms. And when the water spills out, the water ends up with a mass of 2. So 2 kilograms of mass due to water overflows. So these are our 3 questions. And we're going to try to answer these questions real quick. Alright, so what is the weight of the water that overflows? So here's my beaker, right? I'm going to take this little rock, put it down in there. Now before I've done that, it's suspended by this cable, right, that's attached to my spring scale. These are my 2 forces. When it's just hanging in air, I have a tension force up, and I have the actual weight of the rock going down. So those are my forces. And can we figure out what this actual weight is of the rock? We can. It's pretty easy. It has a mass of 3 before it is lowered into the water. So what do? So what we do is we do m times g to figure out what is that downward actual weight. M is 3, g is 9.8, 3 times 9.8 is around 29 point something, right? So this is our actual weight of the rock. So that's good to know. They're not going to just say, hey, solve for the actual weight, but you know that if you draw forces, if you approach problems by saying, can I draw a picture, maybe a free body, which buoyancy problems are all free bodies for God's sakes, right? Then I can get going. Now when we lower the rock down into the water, what's going to happen? What are my forces? Okay, when we lower into the water, it gets a little more complicated. Okay, so you have a weight going down. I call this the weight on the scale, which technically that's what this was, right? This weight going down is what the scale would read because these two things are balanced. So your tension force is equal to this. So this weight actual here is what the scale reads. Here, this downward weight is what the scale is going to read. Okay, is it going to be the actual weight? No, but it's the downward weight of gravity. There's an upward force, which is the tension force, because it's still attached to the string, so we still have a tension force. But you have another force, which is the buoyant force, right? Because it's now in a fluid, so there's that upward push helping it. So you have these three forces. Okay? What's going on here? This downward force, right, is being opposed by these two upward forces. So when you add those two up, you get this force, right? And I call this the weight reading on the scale. This weight actual over here is what the scale would read, right, before you put it into the water, and it was 29.4. That reading is going to be greater than whatever this is. So what happens is, and this is what we were looking at here, before you put it into the water, it's going to weigh more, and when you submerge it, oh my gosh, it weighs less. So this is called the actual. This would be what we would call the apparent weight. So our apparent weight is equal to this downward force here. Okay. Now, what are we solving for? Let's go back to the problem. All right, what is the weight of the water that overflows? So when we put this thing in there, water overflows. How much water? 2 kilograms. What is the weight of that water? Well, that's pretty easy to answer, actually. So the weight of the water is mg, right? They said that 2 kilograms of water spilled over, so 2 times 9.8 is 19.6. So that is the first question here. What is the weight of the water that overflows when you put the rock in? Okay. Now, what is the buoyant force that acts on this thing? What is the buoyant force? Well, what does this weight of water represent? Okay. If you look at this picture, right, our actual weight was 7 before you put it in the water. When you put it in the water, it goes down to 4. Some water spills out. You see it says it's 3 pounds. And then there's this little arrow here that says 3 pounds. So the amount of water that is displaced, that water is equal to the buoyant force. Okay? So in our problem here, if this amount of water, if this is the weight of the water that is displaced, then this is equal to our buoyant force. This is our FB here. Okay, so final question. What is the apparent weight of this thing when it is fully submerged? So what is the apparent weight? What does the weight on the scale read? Right? There's a couple ways we can do this. Obviously, you could take FB plus FT. So we know what this is. 19.6 is our FB. If we knew what FT was, well, we could figure out what the weight on the scale is, which is our apparent weight. There's an easier way, though, right? So we know the actual weight, what it actually is before you put it in, and we know the we know the buoyant force, right? So what we can do is this relationship right here works very, very well. Basically, the actual weight, right, the down here, minus that buoyant force once you put it into the water is equal to the apparent weight. This is the equation that I tend to use a lot. So here we would take our actual weight of 29.4 subtract our buoyant force of 19.6, and whatever's left over is our apparent weight. 29.4 minus 19.6 is 9.8, actually, interestingly. So this, and in fact this equation should be in one of my slides. Whoops, apparent weight equals actual minus FB. Here it is. Apparent weight equals actual weight minus FB. So it's in that slide right there. So this is a really handy relationship. And we kind of really went through this. We drew some pictures and it looks a little more complicated than I wanted it to be. But anyway, this is a great example of an apparent weight problem.